So you're still listening to that little sound?
Oh, is it still? You mean the?
So you're still listening to that little sound? Oh, see, that's a problem. Got my sound down.
Yeah, that'd be a problem.
That's what happened last time.
I don't hear the fan sound right now.
You don't?
What?
That's
Maybe
good.
solve this stuff.
Okay. Hello, everyone. Today we have a field day.
Here come the puns.
Yeah, we're gonna be looking at. Yeah, well, yesterday we had the Force Go With You. We had the four forces of the apocalypse, and we had what was the other force? A force is a force, of course, and nobody knows what a force is, of course, right? And this time we have a field day. We're gonna look at a field. What is a field? Any idea? Any suggestions?
What is a field? Okay, if you ask a normal person, hold on, let me write that in the
No, that's a football field, or a poppy field, or
a field is an
cocaine
area.
field.
Like an
A region, really
Yeah,
a region when you're looking at something you're talking
area
about.
or region is the same thing.
No, not the same thing.
Region
Area
just
is
sounds like
2D.
a 3D, yeah.
Right, that's the difference.
Okay, but
One is like a
field
volume.
is kind of like a 3D, a region, like a.
And
space.
that's essentially what it's always been, you know. The first guy
no one says the field between the table and the wall. They talk about the distance between. They don't talk about the.
In ordinary space, but yes, in mathematics.
Oh, boy, okay. Take it away, maestro.
Who invented the word field? Well, it was Mr. Faraday, Michael Faraday, and I tried to pinpoint when he invented the word. And it's important because he studied electric and magnetic phenomena, electromagnetic phenomena, at least since the late 1820s, for sure in the 1830s. And he wrote about them quite extensively. What he did was he gathered all his notes because he had given presentations at the British Society there of scientists. And so he gathered his notes and he wrote a book, what was it, in 1846? Or I think he wrote in 1855, but he just got all his notes from 1846. He wrote 3 volumes, each one like 600 pages.
All on fields?
Essentially, because what he did, he wrote about all the experiments he did, and he did all kinds of chemical elements. He did bismuth, iron, cobalt. He worked with a lot of elements. And so he tried to look at what properties these elements had. He was more in that sense like a chemist, trying to figure out, what properties some of these chemical elements had, and if they had magnetic or electric properties. That's what he was investigating. And so that's why he wrote so much, because he actually wrote, his notes. He would do an experiment, then go to the British Society there, I can't remember the name of it now, but it's the essentially the British Scientific Society, and he would give presentations, and a lot of them were hands-on, which is pretty good. I absolutely love that, because he would go there with some chemical and say, look, I'm going to show you a property that I saw today or discovered today. He would do an experiment right there in front of the crowd and says, look, this is what I found, or usually descriptions. And that's what he wrote about, and all these things were logged in the British Society.
Like a catalog.
Yeah, and then what he did, he just took the whole collection and summarized.
Who was this again?
Huh?
What was his name? Who?
This is Michael Faraday. And by 1855, he's an older gentleman by now, and he puts it into 3 volumes, 3 books. And they were published, I think, 1856. And actually, when you look at them, as I'm going to show in a second here, they really date all the way to 1832. He was already talking to the British Society in 1832. And it's important to know that he replaced Davy, who died, and he was the head of the this department where Faraday worked, and Faraday, who was hired by Davy, he just came up there as a errand boy almost, and he took over. And he was the guy who did all the experiments from then on. And he wrote about them. He wrote about them at the British Society of Scientists there. And then he put all these all his presentations together in 3 volumes. That's what we have today from him. And in the 3rd volume here, what I'm going to show here, it's called Experimental Researches in Electricity. And Michael Faraday writes this in 1846 to 1852. He writes this in 1856 or 55, and he just takes all his presentations from 46 to 52, 6 years worth of it. But actually, he's got more time than that. I know he's been there since the 30s, at least. And this is where the first written word magnetic field appears. It's in the 20th series, titled Action of Magnets on Diamagnetic Metals Generally. And he gives this presentation December 1845. And he says there, my test of magnetism was this: if a bar of the metal to be examined about 2 inches long was suspended, section 2249 is the one he's referencing, in the magnetic field, and being at first oblique to the axial line, was upon the supervention of the magnetic forces drawn into the axial position instead of being driven into the equatorial line or remaining in some oblique direction, then I considered it magnetic. So again, he was looking at different types of materials and whether they were magnetic or not. And the only thing that makes me doubt that, as you can see, he uses the word magnetic field very casually, like, oh, you know what I'm talking about, right? And so he was using already the word field, magnetic field, the term magnetic field from way back when. And here,
it feels more like everyone was, or else he would.
Yeah, right. They were all familiar.
It feels like a common parlance at that.
Correct.
It says it so offhandedly, like, oh yeah.
And here is proof. As always, we need to provide proof. And in that same book, in the 3rd volume, in sections 23, 29, he said, by reference to the 2nd series of these researches, and he puts as a reference section 160, and down at the bottom you see, well, it's 168, I guess. It says philosophical transactions. That's what it was called, 1832. So. Yeah, philosophical transactions was where he would go to the British Society and he would give a presentation. Those were called philosophical transactions. And so they collected all these philosophical transaction presentations. And you can see this one dates from 1832. And you could say that the term magnetic field probably extends all the way to 1830s at least, I would say, but he uses it for the first time in 1845 officially in a written format, right?
Real quick, as a side tangent,
yeah.
Real quick, is the word field ever used for anything besides magnetic field?
Oh yeah, we'll get there. We'll answer that question real quick. Okay, but Faraday never provided an exact definition of what he meant by field. He insinuated that this is a field, and you know what I'm talking about. I'm talking about that region between 2 magnets, and it was something like that. It was very informal, and it was not until what's his name, Lord Kelvin, William Thomson, who comes up with the definition in 1851, and he defines a field as follows: magnetic field, by the way, any space at every point of which there is a finite magnetic force is called a field of magnetic force, or simply a field of force, or sometimes a magnetic field. And he says that in his article on the theory of magnetic induction in crystalline and non-crystalline substances, 1851. So that's when it's formally defined. And in the Oxford English Dictionary, 1884, you see a definition based on it, a more qualitative one than this mathematical notion that people had in their minds. In physics, a body which is within the range of action of another body is said to be in the field of that body. And essentially, what they were saying is that this was the qualitative version of field. What is a field? Well, it's a region of influence that surrounds a body or which influences a body at a distance from it.
So it could be talking about gravitational field too.
Yeah, and
With that definition.
And the interesting thing about gravitation is that the concept of field, not the word field, but the concept that there was a point particle or a body or whatever that carried this halo around itself, that went all the way down to Newton. Newton had disposed of the ether. He originally believed in the ether, and after 10 years at least after he wrote his book, which was I think 1687, so around the turn of the century to the 18th century, say that right? Yeah, to the 18th century, he disposed of the ether. He started believing less and less in the ether, and he had this notion that every body, every particle had some kind of halo around itself, a cloud that surrounded it, and if you came within the region of influence of that halo, you would be influenced by it. You would be attracted, or at least the mathematics indicated that, you know, the more you approached, the more you were influenced by that so-called field. He didn't call it a field because they didn't have that word at the time, but the concept already dated, at least since the days of Newton. I'm sure it dated even before him.
Essentially talking about an area of influence, or what was the word you used? Not area, but
a region.
A region of influence.
Correct.
Yes.
But keep in mind that in the case of Newton, he was talking about gravity. When we come to Faraday, he's talking about magnetic field, and you know, people like that word field, and they eventually, I don't know who did, because I looked it up and I couldn't find who was the first to use it in a gravitational context, but I'm sure it was in the 19th century, and it must have been anywhere between the time that Lord Kelvin defined the term formally and the end of the century. It's got to be in those 50 years. It's got to be from 1850 to 1900. Someone finally extrapolated that same concept, that same notion to gravity. And I couldn't find the paper. I looked and looked and looked, but so far I haven't been able to find it. But
you mean extrapolated it to magnetism?
No, it was already magnetism by Faraday. Faraday already used it, but the concept of field already existed since the days of Newton, but nobody put that word field to it. Okay. And after Lord Kelvin defined it, I think that's when people started, you know, tying loose ends, and they said, well, you know, this region around a magnet, we also have a region around, you know, the Earth or whatever object, according to Newton's equation, gravitational equation. So everything's got a field, a gravitational field, but that gravitational field is not the same as the magnetic field or the electric field.
Well, hold on. As a side tangent to this, when you're talking about fields or regions, it's finite, right?
No.
Okay, then never mind.
That's another one. No, it's good. Good question. Because the electric field is considered. That's another one. You know, you got to think about that, because the electric field is considered to be infinite. That's the word they use.
I was thinking more along the lines of gravitational field is infinite.
Also.
But do they consider it infinite?
Yeah, mathematicians consider it infinite. They never went to the end of the universe to find out if the field of this atom is still over there. But all of this is taken to be infinite. In other words, we don't know where the field ends, whether the gravitational or the magnetic field. They go and they say, well, you know, it trails off because we can't detect it, but we're sure it continues. We just can't detect it. And with electric charges, they say the field is infinite because, you know, no matter where you take the other charge, there's always a connection between them. You know, this field reaches all the way to that field, and you say, well, you know, the field extends infinitely, and that's why, you know, the other charge can sense it.
Is that all there was to the background, to the history of field?
Yeah, essentially that is it. No, there's a couple more things, and that's, you know, we get to the 20th century, and you know, the word field now goes into gravitation specifically. You know, they don't care about the field of magnetic field, electric field, because that was taken care of by James Maxwell mid-century, a little later, 1864 thereabouts. those who take, and people like Hertz, right? And at the turn of the century, they, for sure, at that point in time, they use it to describe the gravitational field. At that point, it's already part of the vocabulary. Again, I don't know when that concept started, when the word field was applied to gravitation specifically, but it's got to be between 1850 and 1900. Anyways, so what is a field today? Well, the definition says in physics, this is from the wiki, in physics, a field is a physical quantity. A physical quantity. Listen to what it is. That's in physics, okay? Represented by a number or tensor that has a value for each point in space and time. Okay, so what's a physical quantity?
Yeah, that's...
And here we get now you get an idea how mathematicians define words, why they have trouble, okay? Here's a physical quantity. A physical quantity is a physical property of a phenomenon. I like it. A physical quantity is a physical property. Great. That's the definition of a phenomenon, body or substance that can be quantified by measurement. Or we can say that quantities which we come across during our scientific studies are called as the physical quantities. Okay, so a physical quantity is a physical property. And what is a physical property? There we have it. Physical property is any property. I like that. I say physical property is a property. Okay, great. The property that is measurable, whose value describes a state of a physical system. The changes in the physical properties of a system can be used to describe its changes between momentary states. In other words, what they're looking at is changes in states of a system. If they can measure it, they call it a property. If they can quantify, it's a physical quantity, and that's what a field is. It's a physical quantity, no, that you can quantify, right? And that's what it is. A field is a physical quantity represented by a number or tensor that has a value for each point in space and time. What are they saying? They're saying that around a magnet or around the Earth, if you're talking about gravitation, for example, there's a region. And each point in that region has a value and a unit behind it. If you're talking about gravity, you're talking about, gravitational units. If you're talking about...
Hold on, real quick. When you say each point has a value,
yeah,
that's not really correct. It's each point is given a value.
No, each point...
Is humans giving it values to each point in space.
Well, okay.
It's not like Mother Nature has a point in space there that we're reading from. It's like each point is given a value because we need to measure. It's like if I give this this table a value, it doesn't mean it has that value. It's just I'm giving it a value. Values are given. Not
yeah, but hold it. Let's understand that exactly. Yeah. Okay, you're right to some degree. In other words, we assign a value to it. I'm sure if we go to the planet Klingon, or Mars, the Martians, they probably have other values over there, right? That's what I've been told by the Martians. They visited me a short while ago. And, so values, yeah, they're artificial. But the issue here is whether there is a potential there. See, you got to measure something. That potential has to be there for you to measure. Okay. And what they're saying is that the potential is already there. What they're doing, assigning a value, they're saying, look, so many, so much tension, so much force, so much gravitational attraction. This is the strength at that point, and they assign a value, but that strength already is there because they're measuring it.
So what they're trying to say really is every point in space is measurable,
right?
And you can tell the difference between every other point in space,
and you can assign a value to that point. In other words, if you look at all the points around the moon, they're going to be different than all the points around the Earth, simply because they're two gravitationally distinct objects. Okay. And same with magnets. If you have a higher magnet, where's our magnets? Oh,
they're gone.
No, they're not. Here they are. See, here these magnets are.
Those have a weird shape.
Yeah, well, no, I requested horseshoe.
Yeah, but I think only the tips.
So these are very strong magnets, and you got to pull them apart But there's a strong gravitational field in us. And you take two small magnets, like the magnets that you use in the fridge, and you don't have to pull them apart like these.
Magnetic field, not gravity.
Magnetic field. You can pull those apart very easily. And that means that, the value at each point in space around those magnets are not as strong as the values around these two magnets. And that's another issue that you got to keep in mind. That
we're still talking about quantification. We're talking about
correct.
There's more something.
More something.
Yeah.
That's the way to put it. No, but not only is there more something, what I'm saying is you can measure and say, look, this is what my detector says. Fine. But the point is, there is a value here. There is already a value there. And all they do is just measure and give it a number and a quantity, and they say, okay, so what does that number and quantity mean? Well, it's a relationship with one that has less.
Yeah, but I still bristle at the fact of saying that there is a value there. It's not that there's a value.
Not
there.
value, right?
There's a force there,
correct?
Whatever you call it.
And we're quantifying.
There's a happening there.
There's something. There's an event. There's an event.
Yeah, there's an event there.
And we're quantifying.
And we're quantifying.
Right, correct. That's
and
the way
we can tell that this event has more something than the ones from the magnetic fridge.
Correct.
From the crappy magnets.
And that. Is that what they are?
That's the vaguest.
Well, they work. They hold the paper up there.
That's the most specific you can get with the vague language.
So
okay, so we have a quantifiable field. What does that help us?
Well, what it helps us is that then we have Mr. Einstein. He comes up with a what is called the field equations. He comes up with that in 1915. Let me see if I can move aside here. 1915 paper. I think it's published in 1916. And November 1915 he published, I think. Yeah, it was at the end of 15. And he says, in theoretical physics, that's what these equations are today, right? And applied mathematics, a field equation is a partial differential equation. So an equation is an equation. Okay, I like that. They always define using synonyms, right? Which determines the dynamics of a physical field. I like it because they talk about a physical field when they say, well, a field is a region to which we can apply numbers, and here they're talking about a physical field. Well, what do you mean a physical field? I thought you said a field is an abstract concept, and so how can
it's a number line or like a map,
right? A map
is different than a ball or like a force field or.
But it's a map. That's what it is. Essentially, they're mapping this, specifically the time evolution and spatial distribution of the field, and. Since the field equation is a partial differential equation, there are families of solutions which present a variety of physical possibilities. Okay, so essentially that's what a field equation is. What Einstein comes up with his field equations. He says in general relativity, the effects of gravitation are ascribed to space-time curvature instead of to a force. Yesterday we dealt with force, that's Newton. Einstein deals with fields. And you say, okay, so what is a field? Well, a field is a potential at each point in space. That's at least the qualitative definition of it, right? But that's not what general relativity uses it. They call field something else. They refer field to space-time and to a bunch of equations that really are not related to a potential at each point in space. They say the starting point for general relativity is the equivalence principle. We covered that a while back, which equates free fall with inertial motion. Fine. The issue that this creates is that free-falling objects can accelerate with respect to each other. In Newtonian physics, no such acceleration can occur unless at least one of the objects is being operated on by a force. Okay? So you have to have a force applied. But in general relativity, they say you don't need the force to get that thing in, moving, accelerating. But you do, because again, we have that problem where, the ball or the planet or whatever wants to fall into the depression, into this region that has a big gravitational potential. Why does it go down? I mean, why does it fall into the depression, not upwards? And again, the mathematicians say, well, that's just the best we can illustrate it, the best we can represent it graphically. in order to really understand it, you can only understand it mathematically.
Well, I think it's because they use equations that are actual Boole equations. They actually take the curvature equations and say, okay, if we use the Boole equations, it all works out, so it must have some sort of Boole metaphor.
Right, and that's the issue. The Boole metaphor is not supposed to be taken literally according to the mathematicians. You're not supposed to take it literally. You're just supposed to, that's only a graphical representation, more or less a ballpark thing of what they're talking about, right?
But I think it's because they actually took equations from, like, calculating Boles and curvatures, and they're like, okay, we can use these equations and fit them in here, so obviously it must have Boole properties. Boole-like properties.
But then the issue is we got to give a physical interpretation to what's out there.
Yeah. Well,
and so you can't just tell me, look, there's the sun creates a bowl, a gravity well, and the earth rolls around it. That's your physical interpretation? And they say, well, you know, you really got to take math to understand what we're talking about. That's just an approximation. That's just a ballpark picture of what we, the best way to represent it in words. And you're saying, well, yeah, but I mean, I need to know why the Earth doesn't leave the solar system. And what you're telling me is that there's a wall, a curved wall of a gravity well, a bowl, whatever you want to call it, that prevents the Earth from going out.
I feel bad for Australia. They get crushed while they're rolling around
That's
space.
One issue.
No, but my point is that it's kind of like when we're talking about science, metaphors are at the door. No metaphors allowed here. And when they're talking about analogy and metaphor, when they're talking about a bowl, but they don't really mean a bowl, then say what you really mean.
Right. That's one issue. The other issue is that we have a problem anyways, because the astronauts, you know, they go with their ships all the way to the moon, and here these people are telling you, look, there's a wall pressing against the Earth. The Earth presses against the wall. That's the physical interpretation. Okay. So there's a wall that's preventing the Earth from flying away, because that is their physical interpretation. You can't dismiss that and say, well, you know, you got to take math. No. You're saying there's a wall. And how come the astronauts can go through that wall? And if, you know, so your analogy is wrong.
Because the moon landings were faked. You didn't know that?
Well, maybe the moon landings were faked, but we sent satellites, and they should be crushed by now by that wall.
The satellites were also faked. Everything's fake. But you still gotta
the clouds! Are the clouds faked?
No, but even if everything we sent to space is fake, you still can't. You still have to contend with the fact that we're not crushed against, against the bowl of space while we're rolling around it. You know, somehow we're rolling against it, but we're not touching it.
Yeah,
Australia isn't crushed, you know, or whoever is
I'm not being crushed.
Yeah, whoever is touching the bowl of space, that continent should be a disaster.
Not to mention the people, we should be all squashed like ants against this wall.
I told that to a friend of mine who believes in black holes, and he was like, "Well, no, it's actually you're taking it too literally." Like,
yeah, I know.
Almost like you're making a straw man argument out of it. Like
that's what they consider.
Come on, man. Yeah. Like that's not what they really mean. Like they're not stupid.
Good. Then what do they really mean?
It's a 4D thing, and that's just the closest we can get to talking about.
And this is the problem. We don't have a physical interpretation, and their analogy doesn't work. Their analogy is wrong, because you know the guy says there's a curved wall of space out there, and that's the best analogy he can come up with. And we can say, look, we can go right through the wall because we send probes to Mars.
Oh yeah, it has bowl-like properties, but it isn't fully a bowl. You get what I'm saying?
Yeah, but then give me the correct analogy. Why doesn't the Earth fly out of the solar system?
Well,
what's preventing the Earth from going out? And they're saying it's a depression. Okay, so that's your analogy. Fine, I don't care if it's your analogy is a bowl.
The universe works in mysterious ways.
Yeah, I can just as well say God sends His angels and prevents the Earth from flying away. I can believe that just as much as the bowl.
That seems to be a common problem that you seem to run into when you're discussing online or with whoever. It's like when you really take anything they take to task literally, then people say, no, you're
attacking a straw man.
Yeah, you're attacking a straw. You're just making it look silly when that's not what they really mean. But then it's like they're kind of they're not really putting their money where their mouth is in that sense, because they're not actually saying where they can put their hand in the fire. They're all saying, well, it's kind of like this, but it's kind of not. So they're all kind of
they never pinpoint it.
So they got their foot in the door, but they're also not in it. So when you attack them, they take their foot out. But then when
they say you're attacking a straw man.
When you're not looking to talk to other people or whoever isn't into the subject, they just kind of put their foot back in there and say, well, yeah, it's a bowl, curved space, and throw a lot of things out there that no one really even knows where to start to contend with.
No, and then you have half the population who actually believes that it's literal, and they illustrate the curved wall of space. They illustrate space-time. In other words, what they show is, look, this is the way curvature is. There's a couple YouTube videos showing how space is curved inwards and so on. So the people actually believe that, this is not just mathematics, that it's the physical interpretation of what's out there. And these people actually believe that, and nobody puts them straight. I haven't seen anyone from the establishment go in there and say, look.
Well, but again, I think it really comes back to this thing that you seem to not really notice, because, you take it for granted, but no one else has any other explanation. There's no better one. If I criticize, the establishment, I can't really say, this is my theory, assuming I didn't know yours.
Yeah.
I don't have this kind of pocket
comparison.
Aces. I don't have these pocket aces to whip out and
but if it's irrational,
I can criticize it, but that's all we're left with.
Right,
no theory. And I think everyone kind of has that problem, even in mathematical physics. It's like, I bet a lot of them, I've told you this before, I bet a lot of them are frustrated with the current theories. Like, they kind of tote the party line and say, yeah, this is kind of how it is, but in the back of their head, I think they're kind of like, they can't, like something's missing. And I think
you think they are like that? I have grave doubts about that. I'm such a skeptic about that.
Who really thought things through.
Well, if you know a mathematician who thinks like that,
I'll send them your way.
There you go.
But again, it makes a big difference to have another theory to latch on to
compare
rinse
against.
Your head, to compare it against. Right now, you can compare it against religion, and that's about it. You can compare, mathematics to God, and they're both kind of wacky. And there is another one, which is Newton's, and Newton's was a particle theory. Even though he said, look, I have no hypothesis. Fingo non hypothesis. I have no hypothesis. In other words, he said, this is the way it works. This is the description. This is the mathematical description of the equation. But he says, don't ask me how it works. Don't. And he visualized particles. He thought about the ether also. He even considered waves, because that was a big topic in his days. And he finally couldn't figure it out. He couldn't figure out how the universe works. And today, as you say, today we have warped space, and no one's going to go back to particles, because again, you cannot explain with particles how you keep the Earth tied to the sun. What's the sun do? It's throwing gravitons at the Earth, just pelting it with gravitons, and that's what keeps it tied to the sun. You can't explain with particles. Well,
and that's why Newton was right. Fingo non hypothesis.
Well, that's why I think I put the correct timestamp title here, How Theories Are Perpetuated.
Yeah.
Because that's really how it is.
I discussed that yesterday.
That's really how traditions work in general. Besides theories, just how humans work in general. They kind of just go with the best thing we got.
Yeah, but then
it might not be right, but it's the closest thing to right.
But then what they should never do is censor. They should let all different theories come up. Sir, I'm not an electric universe guy, but I would rather listen to them than have them censored.
Well, yeah.
I think they should be allowed to present their case, and you can criticize it and talk to them and debate. But to have them censored, no, I don't agree with that. I think that's where we do damage to science.
I think it really goes back to the fact that there's too much at stake. Kind of like the system is kind of built to hide anything that could topple the whole thing. Anytime money's involved. When we started this Patreon, I was already nervous.
You think it's all money for these guys?
Not only money. It's money, ego, and status. It's really like
careers.
Careers, yeah, but it's like everything. Because if forget the money, if I believed in black holes for 20 years and I've been telling everyone, look how smart I am, I know about black holes and I can tell you the exact details.
It comes someone,
and then like someone just comes and erases that off the board. Like, everyone who thought about that was dumb. Now you just kind of stand there like looking like an idiot. Like, oh shit, what have I believed all this time?
I specialized in idiocy.
But it's like I'm sorry, but that's just the best we had all this time. So it's like you can't really fault them for that either. That's just the best we had.
Yeah, but you would think that at least they should all recognize that, you replace religion. We had the angels pushing the earth around the sun, maybe, or God doing whatever. Fine. And so you say, well, that's irrational. We don't go for that, supernatural. And then you come up with bigger nonsense. At least you should recognize, look, we don't have an explanation for this. But to say that they do have an explanation, and that they have an explanation because the math backs them, that's a lie. Not only is it a lie, it's a crime against humanity. It's a crime against science, for sure. Well, because they should at least admit that they're ignorant and they don't understand how gravity works, instead of saying, oh, we know because the equations told us. And our theory based on these equations is as good as it gets. No, you should at least say, no, this is nonsense, but we don't have an explanation. We only have a mathematical description. That's the correct way of saying that. Well, and that's not what they do. And again, for what you said, it's careers, money, status, so many things.
Ego, self-image, all that. Yeah. If you're the science guy and someone comes and says there's no science, it's like, hey, what are you left with, But I think that's enough politics for today. Let's go back to the field.
Okay,
let's go about the fields and the bowls.
Yeah,
space.
Yeah, and here we have...
Space is a big dining table with a whole bunch of bowls on it.
Here we have the qualitative notion that we have today also. And you can see how this is all circular, how they're terrible at defining, all mathematicians. Field is a physics term for a region, blah, 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 blah. That comes from the JPL, Jet Propulsion Laboratories, paper called Basics of Radio Astronomy. This is the basics, and they tell field is a region.
With Jet Propulsion Laboratory, these guys actually build rockets.
Uh-huh.
So these guys are actually doing like technology and basing like real people's lives.
But that's the point. The point is that technology has nothing to do with science, because you can be a total idiot in science and be able to work with magnets, and say, oh look, I can pick up iron filings. Look at the magic,
Yeah.
And you say, well, yeah, but you haven't been able to explain how it does it.
Okay, but it's still kind of scary that people who are building rockets, that's billions of dollars or whatever.
They don't need to know. They don't need to know the science of it.
But it's still kind of freaky that they accept regions of space and kind of talk in these weird abstracts that they don't.
It's all like that, and that's what's so weird. That's what's so dangerous, that these people are just juggling concepts. And here's the circular part of that. If you look up the word, so field is a region of space. If you look up the word region, it's a portion of space. And what is space? The infinite extension of field. so we made full circle. These are the definitions you find in the dictionary.
It seems to be a common reoccurring theme with these definitions. Either they're circular or they just define themselves.
And one of the problems there is that the mathematicians say, well, you can't define these words. They're all primitive. All the words in mathematical physics, they're all primitive. The point, the line, field, energy, mass, force, time.
Primitive?
Primitive means that it cannot be defined with more basic terms. Why? Because those basic terms, each one of those needs to be defined as well, and each one of those has words that define them, and each one of those has to be defined. So they say, look, it's all recursive. You can't really define any term scientifically, because you're going to keep asking, well, what is this, and what is this, and what is this, and what is this? And the devil's advocate can just tie you in knots. And that's their argument. That's essentially their argument, that you can never define any term precisely. And that's what's nonsense.
Kind of like saying, since we can't define these base terms, anytime you question the base terms, you're kind of outside of what we really...
Science.
Yeah, outside of what we really need to talk about. Do we really need to talk about what a line is? Let's get to the real science.
Right, and this is the problem. The problem is that physics... science in general requires precise definitions, rigorous definitions. Not of every word in the dictionary. No, we don't need every word. We just need those words that make or break your theory. You know, if someone is going to say, like Stephen Hawking says, you know, space-time is an object and black hole is an object, you got to tell me what an object is. You can't say, well, you know, we can't define these terms. We don't know what they are. You can't say that because you said that space-time is an object and black hole is an object. For me, it's not an object. And so if you say it's an object and I'm saying it's not, then we need to resolve that difference. And for that, we need to define what an object is. We got to go back to the word object. We don't need to define every word in the dictionary. I don't need to define what and means, what or means. I don't really need to get to the... I need to know what an object is, because physics can only be done with objects. I hope everybody agrees with that you can't do physics without any objects whatsoever. If not, watch my first Real Physics installment, and it'll tell you you can't do physics without an object. There's nothing there to analyze, nothing there, no event going on without any object. So the first word any physicist must define in physics is the word object.
Do they have to define that in every presentation?
The way I look at it is, if you're going to write a textbook of physics, the first word you absolutely need to define for the student is the word object. You need to tell the student, look, physics is done with objects, and this is what an object will be for the rest of the course, for the rest of the book, for the rest of my paper,
but
whatever.
Do you think that only because there's just been such a kind of, what do you call it, neglect, such an extreme neglect on defining words, that now you kind of take it to the extreme, or you kind of go, okay, now we have to define it every time. Let's just make that a rule.
If the guy,
so we don't have this problem
if the guy says, if the guy in his dissertation is going to say that a black hole is an object, and I disagree with that,
yeah,
we got a problem.
So
you know, I need to find out, what do you mean by object then? Because I have a totally different notion of what an object is. And if you're saying that a black hole is an object, it's zero dimensional, just a mathematical quantity out there, just a bunch of mass. It's a concept. Then that's not an object for me. And so, you know, we need to decide that, because I can't follow your presentation otherwise.
But wait,
you can't say, well, we don't know what an object, we can't define a term, or it's this or that.
It's not about accepting, it's not about coming to a common ground. Isn't it more about you kind of having to accept his definition? Whether you understand it is a different...
Correct. I don't have a problem with that. I'll accept his definition to understand his theory, but then he can't say, look, an object's that which we can touch or see. Well, we can't even touch or see a black hole. So what do you mean it's a touch or see?
So you're saying that...
So there's a contradiction there.
So whatever definition he happens to
he's got to use it consistently.
He's basically going to mess up somewhere along his theory.
Or he's got to use it consistently. If he's going to say, look...
is that what you can touch? Then this astronaut
an object is that which has volume. Well, what's the volume of a black hole? It's zero dimensional. Now he can say an object is that which has mass. And a black hole has mass. Now he's consistent, right? And then we got to look, okay, what is mass? Well, mass is the quantity of matter. Black hole crushes all matter out of existence. And so we have no matter, but we have mass. Okay. So we have all these contradictions. They have to be resolved. You can't let the guy give his presentation until you really understand what this guy is talking about.
Yeah, but I think it really...
You won't understand. You won't be able to follow him.
Yeah, but I don't think you can really talk about one definition. Because I've told you this many times. The biggest wall you have with having anyone even understand you, let alone accept it, is the fact that to understand, to accept one definition, you kind of have to accept the whole map, the whole web of definitions, to really understand why each definition is the way it is. You can't really take your definition out of context and place it in someone else's thing, because now it won't.
Correct.
It won't make sense. So when you really put a fine point on one of their definitions, you're really attacking their whole web of theories. You start going, okay, what is mass? Okay, if we don't know what mass is, then we don't know what an electron is, we don't know what a photon is, we don't know like 90 things now, and then those have problems on their own. So this web breaks down pretty fast.
That's why I'm saying. The
guy never gets to his presentation.
I came up with the words that I think are necessary to do physics. And you need to know, as far as I'm concerned, these are the words that you absolutely need to know to do physics. And the first one is object. You need to know what distance is, what location is, what motion is, and what existence means. You need those, at least those 5 words you absolutely need to do physics. You know, because if you're going to say something about motion throughout your theory, if you're going to say that this exists, if you're going to say... there's distance between these two, and the distance of this was so many meters. If you're going to say, well, the position, they use the word position, I use the word location. The position of this object is there or here, and there's a frame of reference or whatever. Then we need to have these definitions. You have to tell me what these words mean. And I think you can't do physics without those words. And look up, don't take my word for it, you look up any textbook of physics, high school, college, PhD, you will never, ever find any of these definitions. You won't find what an object is. You won't find, what distance is, the real distance, not the distance traveled. In fact, you don't even have the distance traveled of mathematics defined. Because they say distance, oh, it's a length. And what's length? And length is a distance. To them, it's synonym because they just roll the tape and measure so many meters. And they suspect that, or they insinuate or take for granted that you know what they're talking about. And so I think you need to know what, or to define, the words distance, location, motion, and exist. You need those words. Physics is the science of existence. Physics only studies that which exists. And so you need these words. And that's why I created this foundation, which I said, you got to stick to that foundation. And so when someone touches one of those buzzwords for me, I instantly, intervene and say, oh, but you're doing semantics. You want to do ontology. I want to do science. And they don't realize that science is communication. You got to communicate your theory, your explanation, your mechanism. And if you don't know what these words are for your own theory, much less can you explain them to me. So, yeah, I do harp on language because the people try to skip those words and they think, oh, you know what I'm talking about. What did Newton say? I don't define time, space, motion, etc. because we all know what they mean. Why should I define them? No, you need to define them because otherwise I won't be able to follow what you mean. Your theory.
Or you'll just have like this vague notion. You won't really be able to put a fine point. Like if a question does arise, not about the definition itself, but you might have like some problem, some difficulty understanding, like, I don't know, like the spin of a photon or whatever, and you'll be like, okay, like you're really trying to understand something, and you let him use all his definitions, but you still kind of don't understand, why is it like this? Many times this will happen, I've noticed, where you'll have a question about the nature of what he's trying to explain, but it really comes down to how he defined the word in the first place.
One of those is the word you just mentioned, spin. Everybody says spin and say, oh, I know what spin is. You take a top and you spin it.
Oh,
that's not what spin is.
How is that not spin?
And in quantum, that's not spin. Spin is something totally different in quantum. They insinuate.
You told me about
this. They insinuate that it's what a top does when it spins, but that's not what it is. When you come down to it and you say, okay, exactly, what do you mean by spin? They say, is it like the top when it's spinning? No, not really. And so what is spin? Spin is orientation. In quantum mechanics, when they measure, at that moment in which they measure, they find the particle oriented in a certain direction with respect to another one. And they call that measurement, that detection, they call that spin.
Let's see when they use
and so they use these words of ordinary speech.
Words like that so messy.
It's
like,
so
it's so jarring when you really get down to it. It's like, oh, can you just talk normally so that someone can understand it? But
and they say, and that's when they tell you to take a course in math.
But I think the way they see it, it is so complicated, or they made it so complicated, but it's
because they use the wrong words.
Forget that part. But it is so complicated to them that they kind of have to resort to metaphor when they're explaining to people.
But one thing is metaphor, another one is to misorient you, to disorient you and say...
Misspin you?
Yeah, they say spin, and you say, okay, I know what spin is. No, that's not what spin is. Or they say an object, and you say, well, I know what an object is. No, that's not an object. It's a mathematical object.
Where you kind of go, why did you use that word?
Right. They're using these words, and they say particle, and you say, well, I know what a particle is. It's a corpuscle, right? No, it's a wave function. What? So this is the issue is that they use these terms and they borrow words like particle and spin and and object and so on, and these are not object, spin, or particles. They're talking about something else.
Hold on, I thought today was a field day. We went through politics, we went through definitions.
Okay, let's finish up.
The poor little field.
Okay, here we have. We finished essentially with field definitions. Essentially, that's what it all comes down to. What is a field? And so I decided to show you what a field is. There it is. Field is that shiny part that's moving there, not the magnets, but what's around them. And you know, the funny thing about this object called field, whether you're talking about gravitational or magnetic, is that it cannot do without the object. The field cannot do without the magnets. The gravitational field of the Earth cannot do without the Earth. It's a halo that cannot do without its angel.
Wait, but you're wrong about that. I thought that with black holes, there was no object, but there was a field.
Yeah. But see, the question is that they think there is an object. They're called field, and it's zero-dimensional. It's just made of mass.
Yeah, but
but tell them that. They say it's an object.
The black hole's an object.
Yeah, right. So they use the word object to confuse you again, because they say it's an object. What is it made out of? Well, it's made out of mass. What do you mean an object made out of a concept? Out of weight?
They're saying
it's like the elephant's made out of weight.
They're saying there's nothing there with a lot of weight that's making this, that has this field. There's nothing there with a lot of weight with the field.
Correct.
And that nothing is an object. Because it affects other things, it has this area of influence. That's why they call it an object, because how can a not object
have a
field or affect anything?
Correct, and that's the issue. And the issue is that, and then some people consider the field just a nothingness that's there, just a force, and others believe, like both Faraday and Maxwell, they believed, at least as far as magnetic and electric fields, that they were mediated by moving matter. So they always thought of those as moving matter. In fact, I got that in my second installment. If you look at Real Physics, the video that I put up there.
Moving matter.
Yeah, matter in motion. That's how Maxwell described it. He says, in that region, there is matter in motion.
So in layman's terms, it's kind of like, in that region, there are things.
Physicality of some kind.
Things, balls, ropes, whatever you're gonna call it. There's some shape in there. There's something that's doing stuff. It's not this invisible nothingness.
But since they couldn't ever find what it is today, the conclusion today is that Maxwell was wrong. Oh, yeah. There is no physical entity in a region called a field. It's just a field.
A field.
It just is.
There's happenings there without anything doing
no
the
underlying object.
Yeah, they're saying there's happenings there without anything doing the happenings.
Right.
It's like a ball being thrown.
It's a spirit. I like the word spirit. I love the word spirit for that, because that's what it is. Energy, mass, field, they're all spirits.
It's like a ball being thrown without a person.
Yeah. What is mass? Mass without a physical object. That's what a black hole is. Mass without a physical object. What is a field? Also, it's without a physical object. There's no underlying thing there. But then, of course, if you're not going to put a thing in there, you can explain the mechanism of how a magnet attracts another. Likewise, if you don't put a thing around the Earth in that gravitational field, then you don't have a mechanism for why you fall to the Earth. A parachutist falls to the Earth.
It's kind of like if you take out the whatever object that's supposed to be mediating it, you're basically saying that's just how it is.
Yeah, that's all they're saying. That's how it is. Don't ask. You got to take a math course if you want to understand it.
Not even understand it. Just get close to understanding.
You don't not even that, because it's a description.
Oh yeah.
Again. And just in case, okay, once again, this is the magnetic field, right? Just so you know what we're talking about. That's the magnetic field. That's more or less what it looks like. It's shiny. It's color yellow, and so on, okay? And here's the gravitational field. I showed this a couple of weeks ago.
I bet this one's red.
No, yeah, and here, the gravitational field here is that red, orange, and yellow, okay? The shells there. And what it is that as you leave the Earth, you will find different gravitational potentials. In other words, as you get farther and farther from the center of mass of the Earth, which is that close to the physical center of the Earth, the farther you get away, the weaker the gravitation is. And that's what the red, orange, and yellow is supposed to show there. That's the gravity. And notice that the magnetic field is in motion, whereas the gravitational field is static. There's no motion there, because it's a potential at each point in space. Once you take 1 centimeter farther away, you walk 1 centimeter farther away, you weigh less. You have a different potential. And so it's like you entered the twilight zone. You crossed with your feet, you took one step, and now you have a different weight. You weigh less at that point. So it's like there's this dotted landscape around the Earth, a region of points. And if you occupy one point, it's not the same thing as occupying another point. You're going to weigh less. You're going to have a different weight, a different force pulling you, right?
Well, it's funny because then, in a way, what you're saying is the gravitational field is instant. There's no time lag.
Right.
While with the magnetic field, since it has to kind of, I mean, it's very quick, so we don't really notice the time lag. But essentially, you're waiting until the magnetic field hits you.
Yeah, but the problem there is that you're even wrong in that sense, because what they're saying is that gravity travels at the speed of light or thereabouts. In other words, gravity is not instantaneous according to the mathematicians.
Wait. They mean like like the Earth has to throw the graviton ball at you, and by the time that thing hits you, what the heck?
The explanation goes something like this. Please sit down. I don't want you.
That's just wrong, isn't it? That's just flat out wrong. Like,
it's irrational, not wrong. It's irrational.
No.
They say
hold on. Forget irrational. I got this.
No. Hold on. Let me give you an example. Let me give you an example.
Because because that's just wrong. There's no experiment to be done where gravity takes a while.
There's a thought experiment.
Thought experiment. They didn't do the experiment to see how long.
Well, they can't. Not this thought experiment. The thought experiment is if God makes the sun disappear at this very moment.
Yeah.
It takes 8 minutes for us to find out about it, because that's how fast light is. Nothing can travel faster than light or gravity, and so when you cut the rope of a guy who's hanging from a mountain, and I'm hanging from another guy. And if I cut the rope, I don't fall instantaneously. I have to wait for that signal to reach me before I fall.
I'm pretty sure it's instant.
Well,
with the rope. But I mean, okay, but we're talking about ropes, so that's your theory.
No. I'm talking about just a real live rope. Here I'm hanging. I'm hanging from a rope.
Hold on. The mountaineer. It's instant. There's no time lag. You can make that rope as long as you want.
Well, you just have to film it and find out that. According to them.
No, that's just wrong thought experiment. Ask any mountaineer. If you cut that rope, there's no 0.1 second until he falls.
The mathematicians say that if you cut the rope, it takes time for you to receive the information.
Because they automatically say by default that nothing travels faster than light, except gravity.
And if I cut, if two people pull on a string, and I cut the string, they both fall, right? They didn't fall instantaneously when I cut the string, according to mathematics. It took time for that signal to reach them before they fell. That's
just wrong.
I know, but that's what they believe. And so they say that when the sun disappears, it takes 8 minutes for the Earth for us to find out about it.
That's dumb.
Yeah, and that's what they have. And it takes 8 minutes because the gravitational wave takes 8 minutes to reach the Earth to modify the gravity well. So it takes 8 minutes for that wave
to flatten out,
to come. Whatever. It's coming. It's coming in there, right? And when it reaches us, then we say, "Oh, the sun disappeared." Yeah, that was 8 minutes ago.
It's weird, but realistically speaking, if the sun did disappear, which isn't very realistic in the first place, but it would take us 8 minutes to see it disappear, but we'd instantly feel the gravitational change, right?
You would think.
Talking about, like, realistically, if the sun just disappeared right now, right?
It would be instantaneous.
No, but there's two things. We would see it 8 minutes later disappear, because we're talking about light.
Uh-huh.
But the
gravity
would be instant.
According to them,
forget them. According to you.
Oh, of course. If we remove, we're not tied to the atoms.
So you feel the gravity change,
and you'd never see the light.
Oh yeah, because then
there's no torsion.
That's an interesting point with the 3D modeling thing. Whenever you remove a vector, right? Because there's vectors. I'm gonna give you a little crash course before we end the thing.
Okay.
There's vectors, edges, and faces. I don't know if they use the same thing in mathematics.
Okay.
Or a vector is a point, an edge is a line, and a face is a surface.
Okay. Yeah. More or less.
But whenever you remove a vector, out of like a cube, for instance, you delete the vector, the edges attached to that vector disappear too, because there's nowhere for them to end.
I see.
But I guess the same thing would happen with the sun disappearing, where if the sun disappears, you remove all those vectors, all the lines, all the ropes attached to those would also disappear.
Right. Yeah. I mean, if you just make the atoms disappear, right? Somehow, God goes in there with his magic wand. He just makes the atoms disappear.
By default,
the ropes are suddenly go limp, I would think, because there's no tension.
But I think it would be just like in the 3D program, where you, by default, by proxy, you'd have to take out the ropes attached to them as well.
Well, no, but assuming that God can do, God is all powerful. He just gets rid of the atoms, the atoms, and he leaves the ropes there, right?
Weird.
But then there's no tension now on the rope, so immediately it goes limp.
What does that mean? That gets into weird stuff there.
Well, no, that's more or less like cutting a rope between two guys who are pulling.
Yeah, but
it's more or less like that because the rope goes limp.
Okay, but when you're talking about
and that's instantaneous.
Magnetic rope, there's not really a cutting of a rope.
No, what I'm saying.
There's no such thing as a limp rope.
But that's what I'm saying. That's my point. My point is that if God could make the atom disappear, just the atom, leave the rope there, the rope has no tension now, but that's instantaneous because you made the atom disappear. That part there is instantaneous.
True.
And the question is that if that what is it, the slack, right? That looseness travels, 8 minutes away to where the atom is at the other end. I don't think so. I think it would, get loose instantaneously. The whole rope gets
just like cutting,
just like cutting. I mean, even if there's an atom in the Andromeda galaxy, if I make the atom here disappear, that whole rope has to go limp. And finally, let me just finish up with this little thing here, and that's that there's a final notion of what a field is, which has nothing to do with all the rest. Essentially, it says that a field is one of the components of the electromagnetic wave. Electromagnetic. What is the electric field? Magnetic is the magnetic field. And, that's in the 20th century and also 19th. And now we're replacing it with the 21st century. Not a field any longer, but a thread. 2 threads twined around, DNA-like, and we have our rope. And that's probably more than likely what they've been missing for all these centuries, and that's how Mother Nature really runs her shop. Okay, folks, I guess time is up again, and we'll see you tomorrow, same time, same station. Watch the Real Physics second installment. I mailed it to you guys. I'll probably put it up there again for those who haven't seen it. I'll send it through Patreon, okay? We'll see you tomorrow. Bye-bye.